Today we're looking at AWS Step Functions, which is a way of chaining together different AWS resources, in particular Lambda functions, in order to create an application. The example we'll be using is customers submitting smoothie orders, and we'll create a serverless application that can dispatch those orders to a series of robots that make those smoothies for us. Hi and welcome to Mike Likes Robots, where we share knowledge to accelerate robotics. Let's take a look at AWS Step Functions in the documentation. So here we are in the AWS Step Functions documentation. What we can see from here is that it's a service for providing visual workflows for distributed applications. This diagram gives us an example of what you could use step functions for. That is, checking an inventory to see if there's a product available, billing a customer for the product, and shipping the product to the customer. There's even an exception part in case something goes wrong, like the billing doesn't go through. There are other example use cases, but what we're interested in is how to use it to interact with robots. And to do that, we're going to be using MQTT. If you're not sure what that is or why we're using it, please check out my AWS IoT Core video. I'll link it at the top and in the description. We're going to use MQTT to send an order to a robot to make a smoothie, although we're only using a script to simulate a robot. And we're also going to be using Lambda functions to handle all of the application logic. So if you've not seen my video on AWS Lambdas, I'll also link that at the top and in the description. This is an example of the state machine we're going to be building in this video. If we click the Edit button, we can pull up the visual workflow. And these are the stages of the state machine. We'll go through quickly to understand what's going on. At the start, an order comes in from a customer with a smoothie name for our robots to make. That's going into our getRobot function. The getRobot function is responsible for querying or scanning a DynamoDB table to figure out which robot is available to make the smoothie. If there is an available robot, it will pass the robot's name to the next stage, which is the setRobotWorking stage. What this does is write that row in the DynamoDB table, so the robot is set to working. That means that other parallel executions of the state machine won't try and use that robot to make a smoothie. Once that's done, the next function, tellRobotOrder, will publish an MQTT message to that robot telling it the smoothie name to make. Now there's a key part of this, which is that it's using what's known as activities in step functions. This is a way of pausing the execution of the state machine while an external task completes. In this case, we need to wait for the robot to finish making the smoothie. Another way that we could do this is to write the Lambda function to wait for the robot to finish making the smoothie. But given that we pay for Lambda functions in execution time, and a smoothie could take 5 minutes to make, sitting and waiting for that function to complete would cost us roughly 6,000 times the price. It's much better to make the state machine wait. What happens is, in the message ordering the robot to make a smoothie, it will also include a task token. Then it will wait for something to tell that state machine that the task is complete, using that task token. So the robot will receive the order, it will make the smoothie, and then it will publish a message back saying, I've completed this task token, at which point the state machine can continue its execution and set that robot's status back to online, freeing it up for future executions to use. It then completes the state machine. However, if the robot never receives the message or has some error in making the drink, it never publishes that success message, in which case the state machine will time out. That's currently set to 10 seconds so we can see it happen, but it would be much longer in a real use case. In that case, the row in the table will set to broken, meaning that no other executions will attempt to use this robot, and we can go in and try and figure out what went wrong. It will also mark the state machine as failed, so that we know we failed to make the smoothie and we can take appropriate action. That's the state machine as a whole, and there's a few extra resources that go along with it in order to make it work, starting with the DynamoDB table. This is the same DynamoDB table setup that we used in the Lambda video, again link in the description, and it just has robots 1 and 2 set to online. These are our 4 Lambda functions that we use for the application logic. 3 of these are used by the state machine functions. That is the getRobot function, the setRobot working, finished, and broken functions all use the same Lambda function, and the tellRobotOrder function. There's also a fourth Lambda function, which is required for making the robot able to tell the state machine to continue execution. We can see that further in the IoT rule that makes it happen. And this is our IoT rule. If you're not sure what IoT rules are, check the video at the top and in the description, and you can see more about how they work. But essentially, it listens on this topic filter and checks for any messages saying that a task has been completed successfully. If that works, then it will call the attached Lambda function, which is this function here. And all that does is take out the task token and call the task success API from Step Functions. That is what allows the state machine execution to continue. We can see this better in the diagram shown on the screen. What we can see is that the step function, when it wants the robot to make a smoothie, it will call the tellRobotOrder Lambda function. What that Lambda function does is connects to AWS IoT Core and publishes a message. The message is subscribed to by the robot, so it will listen for that order message, make the smoothie, and then publish its own message saying that it was successful with the task token. IoT Core's rule then calls the sendTaskSuccess function in Lambda, and that Lambda function calls the taskSuccess API in Step Functions. This is the end-to-end system that allows us to call out to any edge device that we want. Now let's test the state machine, see how it works. What we're going to do is run a Python script that pretends to be our robot making smoothies. Anytime it gets an order through, it will wait 3 seconds and then claim that it was successful making that order. We'll also run a script to request a strawberry smoothie from our state machine. The execution takes a few seconds while the robot makes the smoothie. And once complete, we get a full output from the step function. Let's take a look in the console to see how that looks in the visual workflow. In the visual workflow, we can see this executions tab where our execution has just appeared. And if we select it, we get this diagram showing that the successful path was the one that was used, and at each stage what the inputs and outputs were, so that we can see how data is passed between the stages of our state machine. We can also see the MQTT messages if we run the state machine again for another successful run. Here I've subscribed to the hash topic, which subscribes to everything. And we can see that on the robot1 order topic, a task token and a smoothie have been requested. We can also see that after a few seconds, the robot1 success topic had a new message published containing the task token to pass back to the state machine. Now let's try running the function where the robot is not successful. To do that, we're going to cancel the mock robot script. This will simulate the robots being offline, even though the system thinks they're online. Now, when we run the test script, it will wait for 10 seconds before timing out because the robot failed to make the drink it ordered. The status is failed. Again, let's take a look in the console for the results. Our latest execution is listed as failed. And if we take a look inside, now we're on the exception path. Here, the state machine failed, and at this point, the robot was set to broken. We can also see this if we look at the DynamoDB table. Instead of online, we're now listed as broken. And if we repeat this process, it will also set robot2 to broken, which will trigger our other error condition. With our other robot set to broken, if we try and run the state machine, it should fail at the getRobot stage because there is no available robot to make a smoothie. Let's try that out. And again, our execution failed. But this time, if we take a look, we can see that it failed at the first stage, getRobot, because the error message, no available robot. That's our step function state machine working as expected. Now let's take a look at the code that I used to build this state machine. This is the code used to build the state machine. It's available online in a GitHub repository that I'll link in the description. It's based off of the repository that I used for the Lambda video, and in fact it uses the same Rust update status function that I used in that case, only with a couple more possible statuses added in. Let's take a look through the important parts of this code to understand what's happening. This is the main stack for the CDK. Because it was starting to get more complicated with several different AWS resources, I've split them into separate files so that we can see what the dependencies are and how they interact. One key tip for developing something like this is that I would start with a CDK stack, implement the resources that you know you're going to use, and then start iterating using the visual workflow in the console. That way you can figure out how to pass data between stages successfully and what goes wrong when an execution fails. In this case, our execution is working as intended, so we won't do that. Instead, we'll look at the code available, starting with robot table. This is a simple DynamoDB table. All we're specifying is that the name of the robot is the primary key. Next, we'll look at the Lambda functions. This time, there are 4 Lambda functions, as I showed in the console. Each one is built in much the same way. It's built using Rust, and the npm run deploy command that I use to build this stack is compiling the Rust code into a zip file that's uploaded to Lambda. The differences between them are that 2 interact with DynamoDB, so they need the table name, where one is reading from the table to get the available robot, and one is writing to the table because it needs to update the robot status. The third function is the send MQTT function, which connects to AWS IoT Core. This doesn't need the table name, so I'll remove this after recording the video, but what it does need is the IoT data access policy to be able to connect and publish messages. The last function is the task success function, which is the function that tells the state machine that a task has been completed so it can continue execution. There are no extra permissions needed at this stage for the function. In fact, it does need a permission to talk to the state machine, but as the state machine hasn't been built by the code yet, that's written into an extra function to be called later on. The next component in the stack is the IoT rules component. This understands that it needs to be able to call the send task success function. It will listen on the topic filter that we showed before, and it will pull out all the data from the message, which will include just the task token that it needs. Then whenever a message comes in on that topic filter, it will call the function. Lastly, we create the state machine itself. What we do is we create each stage of the state machine as a constant to try and separate it out, and so that we can see the logic of the state machine in this order def constant. So we can see that it's chained as different commands one after the other. We start by getting the available robot, then set the robot working, and if you take a look at the state machine diagram, you'll see how this matches up. We can also see that this error is specific to timeout errors, so we'll only catch timeout errors, not if there's another type of error that happens. The important part of these functions is how data is passed from stage to stage. Normally, the step function stores a lot of metadata about the execution as it goes, and it passes the output from one function to the input of the next function. However, we don't always want that to be the case, so in CDK we're specifying which parts should be passed to the next function, and any extra inputs that are needed for our functionality. We start by saying that all of the outputs from getAvailableRobot are needed, because that's the robot name for us to continue execution. In the next stage, we want to set the robot name to working, and there's a special syntax here where if you want step functions to fill in a field from a variable, then you need to write a $$ on the input field name and a $. So that you can look up from the available information what you need to know. That's why we've got robot name $. This corresponds to $robot name. The next step is a little more special because it's this point where we need the state machine to pause execution until it gets its task token back. We do that by specifying the integration pattern of wait for task token. We also specify that it will time out after 10 seconds if there's no task token success. In the input fields, we use a generated task token, which tells step functions to generate a task token and pass it to the input. That is then published as part of the MQTT message. The final 2 functions are much the same as we've already seen. So that's how we can use CDK to define our state machine and how to pass data between the stages of them. We can also look at the handler functions, which are all built using the same template. The only difference is what happens inside the handler function, as each function is responsible for one small part of the application logic. They're all simple to read and understand. I encourage you, if you're interested, to take a look at the source code for yourself and see if you can work out how they work. And that's our complete state machine function. We've seen how to define it using CDK, we've seen what it looks like in the visual workflow, and we've seen what happens with the success and the 2 error conditions that our state machine can handle. So hopefully you're feeling like you understand step functions pretty well, and if you think you do, I've got a couple of challenges for you. First, you could set up the state machine to retry making the smoothie. At the moment, if the robot fails to make the smoothie for whatever reason, the whole state machine just fails, and the customer doesn't get their smoothie order. You could remake it so that it's dispatched to a different robot instead. Or you could create a queue on the input of the state machine, because if all the robots are doing something, the state machine again will immediately fail. You could make it instead so that orders are queued until there is a robot free before it starts doing the work. So let's wrap up what we've learned so far. AWS Step Functions is a service that allows you to create serverless applications using a visual workflow. We can use it to chain together different AWS resources, and it works really well with Lambda functions, because those Lambda functions can call almost anything across AWS. In this case, we used a CDK code to create a state machine that called Lambda functions to dispatch smoothie orders using MQTT messages to our robots. What's nice about this setup is that our robots only communicate using MQTT through IoT Core, meaning that you don't need to change how they communicate with AWS. It's all using messages, same as before. We also use DynamoDB tables to store the statuses of the different robots, which means that we can take a look at what our robots are doing at any time. And all of this together gives us the advantages of running in the cloud, including logging, monitoring, fine-grained permission control, and being able to change our application on demand. Thanks for watching, and I'll see you in the next video.